So today in Physics 20, we're going to be talking about springs. So this might seem like a lot different than what we've been talking about lately with work and energy, but bear with me real quick. It is actually going to have a lot of direct comparisons with what we've already been doing. Here we go. So today's plan is we're going to do a quick recap of last class, and then we're going to introduce something brand new called Hooke's Law. Not this hook, different thing, right? But anyway, then we talk about elastic potential energy of springs. Then last, we'll talk about something called the work energy theorem. None of that right now probably makes any sense to you at all, but they will all connect with what we are doing not only today, but what we've talked about the last couple days. Let's start with a quick recap though. Here we go. So for a quick review example, a guy in a shopping cart with a combined mass of 75.0 kilograms is rolling down a hill. At a vertical height of 17.0 meters above the bottom of the hill, he has a speed of 3.50 meters per second. Find his speed at the bottom of the hill. Let's think about what we were talking about last class. Last class, we were talking all about the concept of energy. Now, energy, of course, cannot be created or destroyed. It can just change from one form to another. If we think about this question here, he's starting up near the top of the hill, right, at a height of, 17.0 meters, and then he's finding his way down to the bottom of the hill. So think about what kind of energy transformation would be occurring here. When things are falling from a vertical height, what's happening is their potential energy, or more specifically, their gravitational potential energy, is changing into kinetic energy. Now, at the bottom of the hill, you're not going to have any potential energy left. Like all of your potential energy will have changed into kinetic energy because the formula for EP was mgh. And if you're at the bottom of the hill, the height would be 0, right? So what we have to kind of analyze here is what our energy was in total in the first place. So we know at that height of 17 meters above the bottom of the hill, he wasn't just stationary. He already had a little bit of kinetic energy. He was going 3.50 meters per second. He was moving, right? Anything that's moving is going to have kinetic energy. The concept that we're going to have to use here is the concept of mechanical energy. Mechanical energy is just the sum, so equals, oops, sorry, let's just erase that, equals, mechanical energy is the sum of your potential energy plus your kinetic energy, or vice versa. You can do them in either order, right? Now, the mechanical energy of a system will not change. So his mechanical energy at the top of that hill is actually going to be the same as his mechanical energy at the bottom of the hill. That's from something called the law of conservation of energy. Again, energy does not get created or destroyed. It just changes from one form to another. So let's start with at the top of the hill. So up here at the top, we're going to say his mechanical energy is equal to his EP. And remember, EP is mgh, so his mass is 75. G, of course, we can assume he's on Earth, is 9.81. And the height it gave us was 17 meters. And it's nice that they told us it was a vertical height. If that was like a diagonal height, we'd have to use trigonometry. That they would have had to tell us what the angle of the hill is or whatever. But they told us it's a vertical height, so that made it much easier. Anyway, then kinetic energy. So plus kinetic energy, in case you've forgotten, is 1/2 mv squared. So we'll go 1/2. His mass was 75. And then his velocity up at the top of the hill was 3.50. And don't forget to square that. So I'll save you the trouble. I'll throw this in my calculator. The answer I got for my EM at the top of the hill is 12,967.125. And the units, of course, on mechanical energy are joules. So I'll just put that in there. Now, just keep in mind from the law of conservation of energy, the mechanical energy stays the same throughout the whole system. So if we move now to the bottom of the hill, that mechanical energy is still that 12,967. What's going to change, though, is our EP and EK values, because our EP is being turned into EK if we're going down a hill. Like I said about a minute or two ago, since we're at the bottom of the hill, we actually know that the EP is now 0. It's completely gone because H is 0. You could throw that into the whole formula. You can go mass times gravity times 0. Myself personally, because I know we're at the bottom of the hill, there's no EP, I'm just going to forget about it. So my EM is still 12,967.125, but that just equals my EP, which is 0, plus my EK, my kinetic energy, which is 1/2 times 75 times their new speed squared, right? So we have to figure out what that new speed is. This 0 is doing nothing, so I'll just cross it out. We just need to rearrange, solve for v squared. So if we times by 2 and then divide by 75, long story short, I get v squared equals 345.79. And then, of course, square root that, and we get v equals to 3 sig digs, 18.6 meters per second. So the law of conservation of energy is really useful for these cases where you're changing not only your height, but also changing your speed. So if something is falling down a hill, or if you have a plane that's like, ascending into the air, so it's increasing its height, these are really useful cases for this, right? There's other classic ones, including like a skateboarder going through a half pipe and then saying like, okay, if they have a height of this and they're going at a speed of that, you can find their mechanical energy at one location, and then you can use that mechanical energy throughout the whole thing. Anyway, I'm not going to ramble to you too much more here. Let's learn our new thing for today, Hooke's Law. So Hooke's Law is really strangely named because it's named after a scientist named Hooke. It doesn't actually have anything to do with hooks, like the object, right? So don't confuse it with that or anything. But Hooke's Law deals with springs. All springs, so springs like this, all springs have something called a spring constant, which is denoted by the small letter K, and that just tells how sturdy they are. Right? So if you have a really big K constant, or a spring constant rather, if you have a really big spring constant, it's a really sturdy spring, right? So a really sturdy spring might be like the suspension in your vehicle, right? It has to like hold up a lot of weight. So those springs are really thick and sturdy. Whereas a small spring constant might be something like those little springs that you find in mechanical pencils. Those are really easy to squish. So that'd be a really small spring constant. Now springs also have something called an equilibrium position. This is the position that they just naturally rest at. So if you left the spring alone, it's going to sit at that equilibrium position. But if you either compress, so squish, or stretch out a spring, the distance from equilibrium that you either stretched it or compressed it is referred to as x. So in this picture, they're stretching the spring. So that distance from that equilibrium, that's your x. That's just how far they stretched it from that equilibrium unstretched spring. But you could have also compressed this spring. So imagine if I made it like smaller, like this, like if I pushed into it, that would still be an x, right? So it doesn't matter if you compress it or stretch it, that distance from equilibrium is still your x. Now, another thing before we actually dive into this. Yes, Hooke's Law deals with springs, but anything that has spring-like quantities to it, so in other words, stuff like elastic bands, for instance, or even trampolines, or bungee cords, like anything that can be stretched and compressed, Hooke's Law also applies to that. Springs are just what we use about 80 or 90% of the time, but just anything that can either be compressed or stretched, like a bungee cord or a trampoline or whatever, this Hooke's Law also works with it. Now, the actual formula for Hooke's Law deals with the amount of force it takes to either compress or stretch a spring. And that formula is right here. F of a spring, so force of a spring, is equal to negative kx. I'm going to be real with you here. This negative is not really all that useful because remember, with forces, negatives just indicate direction. So if I compress my spring upwards, the force pushing back is pushing downwards. So this is just indicating that your force is opposite in the direction to wherever you stretched it. So if we stretched it down this way, the spring force wants to pull it the other way. That's the idea here. Anyway, let's do some examples. Oh, before we get examples, sorry, I forgot. Elastic potential energy. We got to talk about this as well. So we're not just talking about forces when we talk about springs. We also have to combine this with the concept of energy that we've done the last couple days. So when a spring or an elastic or a bungee cord or whatever is compressed or stretched, there is some potential energy stored in it ready to be released. Energy is not the same thing as force, right? So this is not the same thing as force, but it's just another quantity that we can look at here. The potential energy stored in a spring that's either compressed or stretched is EP equals 1/2 kx squared. Looks very similar to the EK formula if you really think about it, like that kinetic energy formula. But again, this one is for springs. Now, just like with gravitational potential energy, which was mgh, this energy can be converted into kinetic energy. The intuitive understanding of this is probably much easier. Look at this little spring that this person's got in their fingers right now, right? So they've compressed it a bit, they've kind of stretched it down, right? They're pinching it. How do you think they could convert that into kinetic energy? Or in other words, how do you think they could get that thing to start moving? I think we all can kind of relate at some point in our lives. If you had a little spring like this, all you would have to do to get it to move is just let it go. If you let it go, this X naturally wants to release, and the process of doing that would convert this into kinetic energy. So by releasing this, all of that energy that you stored up in that is going to fly out into kinetic energy. So the law of conservation of energy still applies to these springs as well. Now time for an example. So suppose a spring in a pinball machine. So this like little spring and little thing that you pull, right? Suppose a spring in a pinball machine has a spring constant of 6.50 times 10 to the 3 newtons per meter. Forgot to mention a second ago, the spring constant has units. It's just there to let you know, like, this is a spring constant. You don't have to worry about the units too much here. They're important, don't get me wrong, but spring constant is just newtons per meter, okay? Anyway, the spring is pulled back 25.0 centimeters and then released to launch a pinball with a mass of 200 grams. How fast will the pinball launch? Here's what I want you to think. We've only learned two things about springs right now. We learned about their force and we learned about their energy. Think between those two things, force or energy, which one's more likely to lead us to a speed, to how fast something's going? Well, I kind of spoiled it there. It would be your energy, right? Because like we said in the last slide, your potential energy is just going to get converted into kinetic energy. So let's roll with this here. The spring is pulled back 25 centimeters and then released to launch the pinball. So by pulling this spring back, once you release it, all of that potential energy that was stored up in that spring is going to be directed into the pinball and give it kinetic energy. So all that EP that you stored up by pulling the spring back, as soon as you release it, it's going to turn into that kinetic energy for that pinball. So let's start by finding that EP. So the potential energy formula for a spring, we learned it just on the last slide, is 1/2 kx squared. As always, make sure your units are in base units. Newtons per meter are the base units for K, so don't worry about that. I'm more worried about my X. X, of course, is referring to how far you pulled the spring or compressed the spring if you pushed it the other way. That's 25 centimeters. But centimeters are not our friend here. We want to turn that into meters. Long story short, we're going to have EP equals 1/2 times K, which is 6.50 times 10 to the 3, times X, which 25 centimeters is actually 0.25 meters. And don't forget to square that. This is going to give us EP equals 203.125. And that's an energy, so the units on that would be joules. Now, what we can do with this is we can now recognize that all of that EP that you built up by pulling that spring back, all of that 203 joules is going to be converted into kinetic energy. Kinetic energy, EK, is 1/2 mv squared. Since all of this EP is being converted into EK, let's just write that in for our EK. 203.125 equals 1/2. Do we know the mass of our pinball here? We totally do. 200 grams, so that would be 0.200, because that needs to be in kilograms, of course, times v squared. Now it's just a matter of solving for that v squared there. I'll just do this all in one go just to save some time, because I've been kind of dawdling on this one here today. So v equals 45.1, and just think about what units velocity is. It's, of course, meters per second. There we go. Nifty. Okay, so the idea here is law of conservation of energy still applies. So in other words, one energy can just be turned into another energy. Think creatively about what a question is asking for you and what you're looking for. Since we're looking for a speed, that doesn't really come out of a force. The only way you can get a speed out of a force is to figure out the acceleration and then do a bunch of kinematics on that. And there's got to be a better way than that, right? Anyway, here's another one. So suppose a 2.50 kilogram block attached to a spring is revolving horizontally. So it's spinning around horizontally, which causes the spring to stretch. Okay, I think we can realistically think that if you had like a block on some kind of spring, like you attached to a slinky or something like that and started swinging it around, that spring is going to stretch out as you're swinging it around, right? Anyway, the spring constant is 9.75 times 10 to the 3 newtons per meter. If the speed of the block is 4.40 meters per second and the radius of the circle is 0.250 meters, how far has the spring stretched from equilibrium? So a couple things I'm thinking here. If we're looking for how far the spring has stretched, think about what letter that would be. Well, the picture, if you look carefully, it actually shows it right there. A spring stretching from equilibrium, that's X. So we got to solve for that somewhere. Now, since we're dealing with springs, there's only two formulas we've dealt with. There's the one for force and there's the one for energy. X is actually in both of those formulas. So that's not going to be the end all be all that gets us on this one. What we should think about here is, are we more likely to be looking at forces on this? Like, is there another force we can connect this to other than just the spring force? Or is there another energy to connect this to? The only energy that I'm really seeing here is kinetic energy, but I'm not really seeing any conversion from one form to another. This kinetic energy is just going to be constant. You're just going at 4.40 meters per second. So it's not like there was a change in energy on this one. So I'm thinking actually force might be the better way of doing it. And the reason I'm thinking that is, what kind of force would be involved if we're throwing this thing around in a circle? Hopefully, you remember from the beginning of Unit C, that would be your centripetal force. And centripetal force, as you hopefully remember, is never really on its own unless we're just looking for some characteristics of the motion. Centripetal force is almost always just equal to some other force. Well, the other force that it would be equal to here would be that spring force. So F of a spring. We've seen cases where when we swing things around, it's your Fc is equal to the tension in a rope. Well, spring force is kind of like tension in a rope, except springs actually have the freedom to stretch out a little bit. So we can actually define a little bit of an extra characteristic with this. Anyway, let's actually throw our formulas in here. Fc is just mv squared over r. I mean, there's also that really big formula, m4 pi squared r over t squared, but hopefully we don't have to use that one. But mv squared over r is what we usually would use for Fc. And then the formula for F of a spring is negative kx. Like I told you guys before, the negative is just, indicating a direction. You can honestly just ignore it in these cases, but I'll be proper. I'll actually put it in there, negative kx. And let's hope and pray that we can get some numbers in here. So mass, do we have a mass on this one? Yep, we totally do right there. So 2.50. Then velocity, we have a velocity of 4.40. Don't forget to square it. Divided by r. R is the radius of the circle. Well, the radius of the circle is 0.25 meters, so we can throw that in there. 0.250 meters equals negative k. K is a spring constant, so 9.75 times 10 to the 3. And then x is what we're looking for in this one. Okay, so just to rearrange this, we'd have to solve this whole left-hand side. We could throw that right in your calculator and solve for that. Then we would have to divide away this number right here. You know what? Let's just do that. If I solve this whole right-hand side, I'm going to get 193.6 equals negative 9.75 times 10 to the 3 times x. That was an ugly x. There we go. Fixed it. Anyway, divide away that negative 9.75 times 10 to the 3, and you're going to get x equals negative 0.0199 meters. The negative again just indicates that it's stretched away, right? Because the centripetal force is pointing towards the center of the circle. So that means that this must be going opposite that direction. So since it's a negative, it's just away from the center. If you ignored the negative altogether, it wouldn't really change what your answer is. It would just make it positive. I'm not really a huge stickler on this. But again, negative 0.0199 meters, or if you prefer 1.99 centimeters, that works totally fine for an answer. So kind of tricky, but really when we tackle these questions, I want you just to be thinking about what we were given and what we're looking for. In this case, we were looking for x. Differentiating between F and E, like your force and your energy, really doesn't help us on this one because it could go either way. But again, if you look at what you were given, especially stuff like mass and speed, really, I think force is just working better here. Could there be a way you could use energy on this? Maybe there is. Just right now, I'm not really seeing it. But force would be the better way because we're going in a circle. We know all about centripetal force, so we're good. All right, one of the last new things for today is something called the work-energy theorem. Not to be confused with law of conservation of energy, although it is very, very similar. So I want you to recall from a couple of days ago that work is defined as a change in energy. So it's just how much energy is changing from one form to another. That's what work is. The concept that work is force times displacement from a few days ago works well for simple movement, like pushing a block along the ground, but the more technical definition of work is more complex, but also more powerful. When I'm talking about the more technical definition for work, I'm talking about a change in energy. In other words, just how much energy changed from one form to another. Now, the work-energy theorem just kind of takes advantage of this. It states that the work done on a system is equal to the sum of the changes in the potential and kinetic energies of the system. This is a lot like mechanical energy, except instead of talking about how much energy you have in the system as a total, you're just saying we're looking at the change in kinetic, because remember delta means change, the change in your kinetic energy plus the change in your potential. When we talked about EM, mechanical energy, that was just straight up how much kinetic energy you had plus how much potential energy you had, not the change. So the change means before and after, right? So maybe your final minus your initial. Energy is a scalar, so we don't actually care about whether we have a positive or a negative or anything on this one. It's all just going to need to be positive answers here. We don't care about negatives with scalars because it's only going in one direction. So even if your kinetic energy decreased, we still consider this a positive number because there was a change in that kinetic energy. This might make a little bit more sense with an example. Let's start with this one. A car with a mass of 850 kilograms that's initially traveling at 60 kilometers per hour experiences a frictional force of 177 newtons while coming to a stop. Find the distance the vehicle slides. If this sounds like kinematics to you, that's because you straight up could do this with kinematics, right? In other words, you could say, oh, this is my VI, and then I have it comes to a stop, so that's a VF. We are looking for a distance. We were given a force, and when you're like slamming on your brakes in a car, the friction force is actually your net force, really. So F net is MA. You can use your mass, find your acceleration, boom, right? You can just use kinematics and find this. However, I do want to specify that because we are applying a force and making this thing come to a stop, we can actually consider this as a change in energy. So there's work being done. Let me show you what I mean. Since the car is moving at 60 kilometers per hour and then coming to a stop, we're changing all of our kinetic energy to nothing, right? We're getting rid of all that. So there is going to be work getting done here. Now, in terms of potential energy doesn't make any sense here because it's not like we're flying through the air and going to a different height. So potential energy both before and after is just straight up zero here. If we can find the change in kinetic energy, so how much that kinetic energy changed, we could use that to find the work. And then work, of course, is just force times distance. And we have a force here. Let me show you what I mean. So first of all, work, according to the work energy theorem, is just your change in kinetic energy plus your change in potential. There's not going to be any change in potential energy here because we're just driving along the ground. Remember, potential energy is mgh, or 1/2 kx squared for a spring. There's obviously no springs here, but because we're not going up in the air, there's no change in potential energy. It just goes from 0 to 0. Whoop-de-doo, right? The change in kinetic energy, though, is the before and after. So before we slammed on the brakes, they're going at 60 kilometers per hour, which we don't like kilometers per hour. Let's divide that by 3.6. That's going to be 16.6667 meters per second. So our before kinetic energy, EK, is going to equal 1/2 times mv squared. So 1/2 850 times 16.6667 squared. Throw that in your calculator, and you're going to get your kinetic energy to be 118,055.5461 joules. That's before we slammed on the brakes. After we slammed on the brakes and came to a stop, well, hopefully you can see your velocity would be 0. So afterwards, your EK is just 0. And it's 0 joules, of course, right? So what's our change? How much did we change by? Well, we just went down by this number. Really, you can find a change just by subtracting these two numbers, but anything minus 0 is still the number you started with. So our change in kinetic energy is at 118,055.5461. Since that's our change in kinetic energy, and since we had no change in potential energy, this is also equal to our work. Our work is just that many joules. Work, of course, is also equal to force times distance. The only force we applied was 177 newtons, so we can say 118,055.5461 equals 177 newtons times distance. And then to solve for that distance, you just divide by that 177 right there, right? So D equals, if you just divide that away, to 3 sig digs would be 667 meters. So Quite a bit, right? But again, a frictional force of 177 newtons is actually not a lot of force. Like you probably could push with more force than that. And the car is going at 60 kilometers per hour. So it's going to take a lot of distance for that thing to come to a stop. So I wouldn't actually say they slammed on their brakes in this case. Probably just more like they gently touched the brakes in this case. It was hardly stopping that vehicle at all. Anyway, I think we got one final question to do here. Oh, and just by the way, if you wanted to do kinematics on this one, you absolutely could. Like, there's nothing stopping you from doing kinematics on this. I can leave that as an exercise for you to try on your own just to double check. I'll tell you right now, I did double check before I started recording this. Kinematics would work just fine on this one. My point of doing work energy theorem is just to show you that that works as well. Anyway, last question. A block is pushed up a frictionless inclined plane. Uh-oh, inclined plane. That's a throwback to dynamics there. But anyway, at the bottom, the block has a velocity of 1.00 meters per second. At the top, with a vertical height of 85 centimeters, the block is moving at 4 meters per second. Okay, so it accelerated. Someone was pushing it up the hill. The block has a mass of 1.20 kilograms. Find the work done on the block. Now, it's entirely theoretically possible, I guess, if you tried doing some kinematic stuff on this, or if you tried doing dynamics, maybe you could find the work done somehow. But we really don't even know, like we don't even know the incline of the plane. We don't know how many degrees this thing is inclined at. This question feels like it was absolutely made for the work energy theorem. So the work energy theorem again says that work, instead of just being force times distance, work is your change in kinetic energy. So how much your kinetic energy changed by plus how much your potential energy changed by. Let's think about this in terms of before and after. So at the bottom of this inclined plane, we know that we had a velocity of 1 meter per second, which means we already had some kinetic energy. So our kinetic energy at the bottom, let's just say EK, is going to equal 1/2 times mv squared. So 1/2 times 1.20 times our velocity, which was 1.00 squared. This, of course, at the bottom is going to give us an EK of exactly 0.60 joules. That was your kinetic energy at the bottom of the hill. Now, at the bottom of the hill as well, just in case you're not clear on this one, we also have like to consider our potential energy, but it's kind of silly at the bottom of the hill because our potential energy, which is mgh, would be 1.20 times 9.81 times 0, which, let's be real here, that's just EP is equal to 0 at the bottom of the hill, 0 joules, okay? At the top of the hill, things are going to get a lot more interesting. So at the top, we still have kinetic energy. As a matter of fact, we have more kinetic energy because the block is now moving faster. So EK at the top of the hill is going to be 1/2 times our mass, which is still 1.20, times our velocity squared, so times 4.00 squared. If you throw that in your calculator, that is going to give us EK equals 9.6 joules. So quite a bit more joules than we had at the bottom of the hill. Now, up at the top of the hill, they were really kind in that they gave us our vertical height. That's always what we need to use with EP. If it gave us a diagonal height, we'd have to do trig on that. But EP is equal to mgh, so mass is 1.20, g, of course, 9.81. The h that we have at the top of the hill now is 85 centimeters, which is 0.85 meters. If we type that in our calculator, what we will get at the top of the hill for EP is 10.0062 joules. So what we need to determine now is our changes. Our change in energy, so I'll just say our delta E's here, is just our difference between the two energies we had before. Now in this case, it's going to be final minus initial, but when you're dealing with these, remember your changes in energy doesn't care about direction. So really you're just going bigger number minus smaller number, regardless of whether you increased or decreased on this one. We increased on this one, so it's still whatever, final minus initial, but always just do the bigger number minus the smaller. So our change in kinetic energy, our delta EK, is just going to be 9.6 minus 0.6, which of course is just 9.0. So delta EK equals 9.0, 9.0 joules to be exact. Our change in potential energy is even much easier to see. Notice how we started with nothing in terms of potential energy and we ended up with this 10.0062. Well, I don't even have to do an equation on that one. It's just our delta EP is just going to be that 10.0062 because that's just how much energy we gained in terms of potential. To finish this whole question off, work is just this sum the sum, adding together of our change in kinetic plus our change in potential. So it's just going to be 9.0, that's our change in kinetic, plus 10.0062, that's our change in potential. Long story short, to just 2 sig digs, because notice right here that 85 centimeters is just 2 sig digs. This is going to give me 19, and work, of course, is measured in joules. Woo! Okay, so that was a longer lesson than I was expecting. I apologize for that. But for some practice, the assignment handout from last class would be the best bang for your buck. You can now complete questions 1 to 7. You will be able to complete the last 2 questions on that assignment after next class, so just hang tight on those last 2 questions, question 8 and 9. For some non-summative practice, or so practice that isn't being marked, Hooke's Law and Elastic Potential Energy worksheet in the worksheet booklet, that would be really wise, as would the Work Energy Theorem worksheet. These 2 worksheets are actually shorter than previous ones. It would actually be wise to do these before you tackle the ones in your summative assignment. So just to make sure that you know what you're doing before you hand in something for marks, right? So they're not just there for decoration. You really should be doing a lot of those questions. You'll be doing a lot or really well in this course if you make sure that you're doing those questions and checking your answers. Anyway, that's it for today. If you have any questions, just let me know.